as we did yesterday. We looked at an example where you went to a very popular restaurant and it was really busy, and they gave you one of those little bus things, right? And they told you that it's going to be somewhere between 5 and 25 minutes. That's what we did yesterday. So if we wanted to come up with a probability distribution that encapsulated the idea that the waiting time is going to be somewhere between 5 and 25 minutes, and that any interval of time that is equal, any two equal intervals of time are equally likely of occurring, meaning that if you want to know what's the probability that you get called between minute 6 and minute 8, it's going to be the same answer as minute 21 and minute 23. Guys, can we stop? So this is a 2-minute window of time here, this little gap right there, and this is a 2-minute window of time back there. So those two are two intervals that are equal in width, so I want both of those to be equally probable of happening. So in order to do that, we do this. So we capture it like this. It's going to be one big rectangle where the picture above, right, so this is the possible values, and the picture above it describes the probability that we would get such an occurrence. So for instance, going back to chapter 6 when we had discrete probabilities, they looked like this. We had maybe a rectangle that went like this, and another rectangle like that, and another rectangle like that, and another rectangle like that, and like that. So maybe we had rectangle like that. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could have something that looks like this back in chapter 6. And so if this was a probability distribution, then that means that all the possible outcomes are listed. So in this case, it's like 0 through 11. In discrete random variables, there were no decimals or anything. So it was just the probability that x equals to 4 or 6 or 2. There were no decimals allowed. And then the picture described the likelihood. So if I wanted to find, for instance, the probability that x was greater than 6 but less than 10, well, in this case, this is the same thing as the probability that x is greater than or equal to 7 but less than or equal to 9, right? Because it's strictly less than 10, so that one. So in a case like this, what we'd have to do is find these areas, the 7, the 8, and the 9. The sum of the areas of those three rectangles would give us that result, right? So you would be given values in the vertical axes to be able to figure out those. So the statement might say something like the height of this one is 0.04, the height of this one is 0.09, the height of this one is 0.05. So then you just add all three of those up, and you'd say that this is equal to the probability that x equals to 7, plus the probability that x equals to 8, plus the probability that x equals to 9. And so x equals to 7 is 0.04, plus 8 is 0.09, plus this one, which is 0.05. So you add them all up and you get 1318. So there's an 18% chance that x is either a 7, an 8, or a 9. Right? If this is going to be a proper probability distribution, all of them have to add up to 1. So then you'd have to find all the other numbers, or they would have to be given to you in a way to show that all of them add up to 9. Good? Okay, so this is what we did with discrete random variables. But now, back to where we are. Now we're with continuous random variables. Now with continuous random variables, decimals are allowed. So it's not just 6 and 8, it's 6.01, 6.275, right? any decimal number that lands in that little interval is allowed. So we got to come up with the picture ourselves. So in uniform distributions, it's always going to be a big rectangle, and we have to make sure that we make the height of the rectangle a value that makes the whole area of the whole thing equal to 1. So I got to make this equal to 1 over 20, which is equal to, as a decimal, 1 over 20, which is 0.05. Right? Questions? 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 No? Okay, so now back to the, oh yeah.
So why is it 1 over 20?
Oh, because the width here is 1 over 20.
Oh, okay.
Excellent question, yeah. So it's about the fact, the reason why it has to be 20 is because this width is 20. So when I find the area of this whole thing, area of the entire rectangle is length times width, so it would be 20 times 1 over 20. And so the whole thing equals to 1. Okay, so now we're back to answering questions about individual results. So now if you want to find the probability that x is between 6 and 8, x is greater than 6 but less than 8, well, pictorially, this is kind of messy, so I'm just going to redraw it again. This guy is going to look like this. I have a rectangle like that, starting at 5, ending at 25, and then I have something here at 6 and going out to 8. So I want to find the area of that little blue region. That will give us that. Okay? So P of x there, that's going to be equal to the width. Well, the width is just 2, which I find by subtracting 8 minus 6, times the height, which we said was 1 over 20. Right? And so this is equal to 2 divided by 20, which is equal to 0.10. So there's a 10% chance, this guy in here is 10%. There's a 10% chance that the random variable x will land between 6 and 8 when we have a uniform distribution described by this. Okay, so a little buzzer thing, there's a 10% chance that it'll buzz between minutes 6 and 8. Is it inclusive? Remember that when we're dealing with continuous random variables, the probability of any individual number is always 0. So whether or not you include the endpoints doesn't matter in continuous random variables. So the probability that x is greater than or equal to 6 but less than or equal to 8, well, that's the same thing as the probability that it is strictly between them. They both give you the same answer. The last little endpoint doesn't matter. They're both going to be equal to the same thing, 1.010. Right? That's very different from the previous one, because when we're dealing with discrete, the endpoints make a big difference. Do we include the 10 or do we include the 6? That could make a very big distinction in your final answer. So here, when I wanted to find the strict ones, not the equal ones, then that's why I said, well, if it can't be 6, it's got to be strictly bigger than 6. The first one it could be is 7, and it's got to be strictly less than 10. The first one it could be is 9. That's why I only included 7, 8, and 9. If this had been equal to, then I'd have to throw in the 6 in there. Okay? So with discrete, it makes a big difference whether or not you include the endpoints. But with the uniform ones, it doesn't matter. Okay? Questions, questions, questions? Okay, so now let's find these, and it should verify that we should get the exact same answer, because any two intervals that are the same width should have the same probability in uniform distributions. That's the whole point of uniform distributions. So, probability that x is greater than 21 but less than 23, well, that's going to be the base times the height of this rectangle right here. So 21, 23, 25, 5, 1 over 20, draw this guy right in here. Right? The picture is very important moving forward because when you want to know the odds that x lands between 21 and 23, it's the picture that tells you the area which is proportional to the probability that you're after. Okay? So pictures are worth more than half the points on the test. Let's finish this up and I'll show you what the point distribution would be. So in this case, it would be this rectangle right there. The area of a rectangle is equal to base times height. It's the general formula for any rectangle. And the base is this, which is just 2 units. It's equal to 23 minus 21 times its height, which is equal to 1 over 20. And so in this case, it's again equal to 2 over 20, which is equal to 0.10. So again, we can see that anytime we have a width of 2, we're going to get an answer of 10%, since this thing is always 1 over 20. Right? So any 2 intervals that have the same width are going to have the same probability. Good. Any questions?